Hello everyone. It's a great honor to be here representing Perfect World Games at GDC 2026. My name is Yizhe Chai, and I'm a graphics engineer at Perfect World. Today, I'm incredibly excited to take you behind the screen of our latest project, Neverness to Everness, or NTE, a next-generation urban open-world RPG. NTE is designed from the ground up as a multi-platform experience, spanning across PC, console, and mobile. Our vision is to deliver a consistent, high-fidelity world regardless of the device you play on. However, bringing a massive Unreal Engine 5 metropolis to the palm of your hand presents a formidable and unique set of technology challenges. That is why today's session will focus specifically on our mobile optimizations. We have a lot of ground to cover in 1 hour session, so let's get started. First, let me introduce myself. My name is Yizhe Chai. I'm a graphics engineer at Perfect World Games. I've been part of the game industry since 2019. During my career, I have had the opportunity to work on 3 major titles that have defined our technical journey at Perfect World, including Tower of Fantasy, G-Dynasty 2, and this one, Neverness or Everness. Today, I'm excited to share our latest journey with Neverness to Everness. We will look at how we leveraged the Snapdragon platform to transform the massive technical demands of a UE5 urban open world into a smooth, high-fidelity experience for players. And this is today's agenda for my talk. We will start the project overview to establish the urban paradox we faced. Then we will move to foundation of our technical stack, memory architecture, where we will discuss their memory heap integration. From there, we will look at the visual layer, specifically how we utilize the Snapdragon Elite gaming features to reach 90 FPS. We will then cover system-level optimizations like SDOC and SHC, which ensure long-term stability. Finally, we will wrap up with the results and what it means for the future of UE5 on mobile. Before we dive into the how, let's talk about the what. Neverness to Everness is our latest supernatural urban open-world RPG. The heart of NTE is the city of Hathor. Unlike a typical open world with vast natural landscapes, Hathor is a dense, vertical metropolis. From a graphics perspective, this means we are dealing with extreme geometry density, complexity, light material interactions on surface like wet asphalt and new glass, and thousands of jokers for street-level details. Okay, let's take a look at the technical constraints that we had. We have a short video clip here that was released recently. It's an actually drone view recording flies through the heart of Hathor. Let's check it out. Okay. To understand our optimization journey, we first need to look at what we are trying to achieve with NTE. We aren't just build a mobile game. We are building a dense supernatural metropolis called Hathor. From a technical standpoint, this is a perfect storm of challenges. We have a high-speed physics of racing game, the precious time of an action RPG, and the massive joke core counts of a modern urban open world. The following sections, we will show you how we leverage the Snapdragon's architecture to ensure this ambition didn't melt the user's phone. UE5's word partition is the backbone of Hathor, allowing us to build a seamless city that feels truly vast. However, the heavy rendering pipeline of UE5 is a double-edged sword. It demands massive GPU bandwidth and generates significant heart of mobile SOC. This challenge is exactly what drove our deep collaboration with Concom to optimize the Snapdragon architecture at the system level. The urban environment is fundamentally different from the natural wilderness. Its objects density and occlusion relationships are far more complex. This complexity is core constructions we had to resolve. To overcome the urban paradox we discussed in previous slide, we entered a deep strategy partnership with Concom. This was not just about driver updates, it was about synchronizing software and hardware. Our goals was clear. We didn't want the game just to run. We wanted it to be silly smooth even in the most demanding areas of Hathor. To achieve this, we built a roadmap that covers the entire stack, including tier memory heap, SGSR, AFME, and SDOC. Okay, let's dive into the foundation of this bridge, the tier memory heap. Now, let's move into the first pillar of a technical collaboration, the physical layer. In a traditional modern rendering setup, the bandwidth war is our biggest enemy. No matter how much to optimize your shaders, if your data is constantly traveling back and forth between the GPU and the system RAM, you will hit a similar ceiling. To break this cycle in NTE, we utilized the working and circle QCOM tier memory heap's intention isn't just an incremental update. In the next few slides, I will show you how we realize our UE5 mobile deferred pipeline to treat GMM not just a temporal cache, but as a persistent high performance residency for our most bandwidth-heavy data. To truly understand why tier memory heap is such a game changer, we have to look at the original high-performance memory architecture. As shown here, this specific memory sits directly on SoC, providing a high-speed highway for data-heavy tasks like gaming, machine learning, and image processing. By leaving these dedications on chip residency, we can reduce total power consumption by up to 10% in real-world gameplay. So, what exactly is tier memory heap? At its core, it's a hardware-software synchronizing designed to solve the most expensive part of mobile rendering, moving data. For a project like NTE, this is absolutely critical. This isn't just a software trick. It's a platform exclusive capacitive enabled by the latest generation of Snapdragon 8 Elite hardware. Essentially, we are moving away from automatic memory management and into a world of explicit control, where we decide exactly how long a resource stays in the fastest memory possible to ensure peak performance. To truly turbocharge NT on mobile, we moved beyond standard memory management and utilized the working concomitant memory cable extension. As you can see under our core mechanism, it isn't just a minor tweak. It's a fundamental shift in data residency. The implementation strategy involves some technical heavy lift. By keeping this massive data flow of the system bus, we achieve more than just the latency reduction. We significantly lower the power consumptions of the memory controller. Where the performance gains are significant, including Intel memory cable into a production-ready game like UE5's presented specific challenges. On the positive side, the bandwidth reduction is a major win. However, we face the real integration challenges. The standard UE5 rendering pipeline often relies on multi-green submit cores, which can break the extension bound of the memory, leading to partition stability concerns that requires careful custom handling. Before talking about the mobile and the base GPUs, let's quickly recap how traditional deferred rendering works on AMR architecture. In AMR pipeline, the base bus has a 4G buffer using MRTs. Once this bus ends, all G buffer attachments has to be stored out to system memory. During the deferred lighting pass, the GPU then reloads those G buffer textures from DRAM, performs lighting, and finally outputs the results. This is exactly where the base GPUs behave very differently, and why a native MR-style deferred pipeline maps poorly to mobile. The tail-based deferred rendering pipeline optimizes the performance by storing geometry data in tail memory initially, maximizing the need to extend the memory access during earlier pipeline stages. However, during the deferred shading pass, green submit describes the on-chip memory flow, pushing the data out to system memory. Its external memory access introduces bandwidth challenges, including velocity pass and post-process pass. The mobile deferred pipeline UE5 is now fully production ready, offering a stable and optimized solution for mobile game development. However, the introduction of external memory access still leads to bandwidth usage during the certain passes. This is where Snapdragon tail memory cable optimizations come into play, solving the bandwidth issue and enable one-pass mobile deferred rendering, a mobile efficient solution for mobile game developers. Okay, now we come to the red game changer, our custom UE5 mobile deferred pipeline on Snapdragon. As I mentioned previously, a standard mobile deferred pipeline is still taxed by external memory traffic every time a queue submit disrupts the on-chip flow. But here, we've effectively turbocharged the architecture using the Snapdragon tail memory heap. By utilizing the working concomitant memory heap extension, we no longer leave our residency to the driver's heuristics. Instead, we have extremely low-level control. We band our scene color, scene velocity, and scene density directly to the GMEM. Look at the flow on the right. Notice how the shortest traffic between the GPU and the system memory has vanished. Because these buffers stay resident on chip across the shading, velocity, and even processing passes, we've achieved what was once considered the holy grail for mobile, a one-pass deferred pipeline. data is the ultimate proof of our optimization strategy. To validate the impact of the time memory heap, we conducted a stress test on the Xiaomi 17 Pro Max in the most demanding urban districts of NTE. By moving our base bus and velocity bus resources to the on-chip memory heap, we eliminated nearly all redundant read operations from the main memory. We reduced the target bandwidth from a base of 47.74 megabytes down to only 40.34 megabytes per sequence. This is a staging 19% reduction in external memory for these critical buffers. Now that we've laid a solid foundation at the physical layer by solving the bandwidth crisis with the memory heaps, it's time to talk about what we did with the extra bucket. In a high-fidelity open world at NTE, the urban paradox isn't just about rendering thousands of objects. It's about making them look sharp and move fluently without melting the device. To achieve this, we leveraged the two powerhouse features of Snapdragon Elite Gaming's SCGSR2 and AFME2. To understand the magic behind the performance, let's look at the core innovation of AFME2. Standard 90 FPS rendering typically demands massive GPU circuits. AFME bypasses this by advancing motion elimination, analyzing motion vectors, and scene content to integrally interpolate frame in hardware. By utilizing these specifically hardware accelerations units on the Snapdragon 8 series, we achieve a lot of fluidity in NTE that was previously impossible with mobile CMOS limits. To truly appreciate the impact of technology, let's look at a side-by-side comparison in NTE. On the left, we have AFME2 enabled interpolating a base 30 FPS up to a CDK smooth 60 FPS. On the right, the game is running a native 30 FPS. As we watch the character traverse through the city in the first half of the video, notice the clarity of the environment and the consistency of motion on the left. We are transitioning to the combat sequence in the second half. The benefits become even more apparent. Oh, sorry. However, it's important to be candid about the technical boundaries. For certain dynamic objects with no continuous or irregular motions, our current algorithm may not handle interpolation perfectly, potentially leading to minor visual artifacts. But don't worry, this is only the half of the story. We've developed a specific solution to address these difficult cases, and I will dive into exactly how we solved those edge cases in the next slide. The side-by-side video we just watched clearly demonstrates the massive impact of ME on the player's experience. On the key benefits side, the most critical one is powerful efficiency. By significantly reducing the same workload on both the GPU and the CPU, we can maintain sustainable 30 FPS performance without hitting the thermal throttling limits that typically plague your mobile open world. As mentioned, the standard motion estimation occlusion failure when faced with no continuous or circle motions like high-speed wheels in NTE. Oh, sorry. Our strategy to fix this was simply in series but complex in execution. If we can't estimate it perfectly, don't estimate it at all. The The standard FME pipeline relies on thin color, depth, and velocity. To handle this strategy, motion edge cases, we introduced a custom velocity mask. Initially, we explored mapping this into the RSB of exceeding buffers, but found precious issues. Our final, most robust solution involved rewriting the velocity path to add an extra R8 texture. This provides a dedicated channel to flag a parametric draw course statically via the material instance by using a CVAR. We can selectively disable the interpolation with specific dynamic objects. To ensure that where the rest of the city stays still smooth and 90 FPS, have wrinkly elements like car rims remain sharp and free of artifacts best of all. We implemented this via platform-specific shaders to ensure zero impact on our PC and metal and console. To wrap up our discussion on frame interpolations, let's look at the final integration results of NTE. Building on the velocity mask solution we just discussed, we successfully integrated the FME into the NTE rendering pipeline using custom hooks in UE5. This ensured full compatibility with our complex post-processing stack while maintaining the visual integrity of Hassel's dense urban environment. Our testing reveals a 35 to 42% reduction in power consumption compared to native 30 FPS rendering. In summary, by combining specific hardware selected with our custom artifact supervision logic, we've achieved a console quality 90 FPS experience on mobile that is both visual smooth and thermal sustainable. Now that we've covered frame generation, let's pivot to visual fidelity. To achieve a high resolution appearance in a dense open world like NTE, we integrated a SDOC. Where Qualcomm and various industry partners have already shared extensive technical deep dive into super resolution across many forums. Today, we will focus on a high-level overview of how specifically empowered the NTE pipeline. To understand the value of SGSR2, we look at the three core pillars: upscaling, innovation, performance impact, and bandwidth savings. When evaluating our upscaling strategy, we found the SGSR2 to be the ideal fit because its performance and quality are strictly on par with the competitive solution. Importantly, it's a cross-platform solution that allows not run specific hardware blocks, giving us the flexibility needed for a multi-platform title like NTE. However, the real value lies in its mobile-specific trailering. SGSR has been optimized down to a highly efficient 2 or 3 pass execution. SGSR has been optimized down to a highly efficient 2 or 3 pass extension. We fully reached the F216 supported, which is significantly more mobile-friendly and performant on Adreno GPUs. In the actual implementation with NTE, we adapt our strategy based on device performance tiers. For optimal quality performance balance, we set the base results to 35% of the target. We developed custom profiles to handle varying scene complexity and ensured a seamless integration with UE's TE system. The results were immediate. We achieved a 12% reduction in immediate bandwidth across our tested Snapdragon platforms, allowing us to redirect those resources into high-quality assets and lighting. Looking at the elementary data, the difference between standard TAU and SCGSR is clear. The top trace shows a high and erratic write-read total for memory bandwidth using TAU. In contrast, the bottom trace with SCGSR inboard shows a much more controlled and lower bandwidth profile. This strategy is key for open-world games. To wrap our discussion on visual enhancement, this by-side comparison demonstrates the final impact of SIGSR2 on the world of NTE. Now, we are performing rendering tricks are great. Managing a massive UE5's open world on mobile relay requires a holistic system-level approach to keep the hardware running at peak efficiency. In section, I want to talk about two pivotal system optimizations we've been integrated and explored in TE: Occlusion, culling, and SAGC. Moving into culling strategy, the sheer density of Heather's urban environment means that a standard solution wouldn't just work out of the box. We spend a lot of exploring different ways to hide what the player can't see to save on rendering costs. In the next few slides, I will walk through the data comparisons we did between the specific methods SDOC, a standard software raster and traditional hardware occlusion queries. We didn't just look at the which one called the most object. We look at the CPU and GPU overhead for each. I will explain why we ultimately made the choice we did to ensure NTE maintains its performance without sacrificing visual complexity. All right. So moving into the system side of things, we really had to tackle the geometric density of Heather. Now, in a typical UE5 setup, you will probably just use hardware occlusion queries. They are executed sure, but on mobile, the round-trip latency between the GPU and the CPU is real killer. It creates bubbles in the pipeline that leads to those analyzing frame status when you are moving those density. One thing you have to keep in mind, though, is that the UE5 mobile deferred pipeline doesn't actually support built-in software culling software solutions. So if you want to go this route, you are going to have to develop it yourself. In our cases, I didn't just want to build something. We wanted to see what worked best for NTE. So we explored two different software paths and compared them against the hardware standard. On one hand, you have a custom SOC, basically a generic C++ raster radar. Then there is Snapdragon occlusion culling. Technically speaking, it's built specifically for the Snapdragon pipeline. It uses new theme to spin up the mask and instead of a full raster radar, and it's used checkerboard rendering to keep the load light. It's also SOC level aware. Mint is tries to stay at the L2 or L3 cache as much as possible to save bandwidth. It even has its integrated rendering strategy to smooth and the CPU load over multiple frames. Now, I'm not seeing one of these massive body for every game. Each has its own overhead. The best approach really depends on your specific scene complexity and your performance budget. For NTE, we had to look at our actual core counts and CPU overhead to decide which directions to take. From our previously technical comparison, this is clear that the SDOC is architecturally superior to a custom software occlusion culling due to its newer optimization and catch-all awareness. Therefore, for our production testing in NTE, we focused solely on comparing SDOC against the standard hardware queries. Here is how we implemented it. SDOC travels the scene every frame to identify occluders and occludees. However, we quickly run into the unique challenges of our open world. In Haswell, we rarely have large single meshes that act as perfect occluders. Instead, the scene is filled with thousands of small to medium objects and instance static meshes. This creates a massive performance headache. If we try to rasterize every object that meets our distance and scene size thresholds, the software restoration cost actually outweighs the GPU gains. To keep the frame rate stable. We implemented an early out strategy to limit the number of occluders proceed. As you can see from the live data on the right, this results is a significant trade-off, where we rendering threads see a performance boost by avoiding GPU to CPU stalls. The culling rate drops dramatically. Our hardware queries are culling over 2,400 primitives, where the SDOC with early out is only catching about 800. This data shows that in dense, highly incident UE5 environment, traditional software culling faces steep uphill battles compared to native hardware queries. To really put the findings from our initial exploration to the test, we run a directly comparison on PC between hardware queries and SDOC. You can see the visual breakdown in the top right image here. When we look at the SDOC performance profile, specifically when using the early out strategy, the numbers tells a very clear story about the trade-offs. First off, the render threads take a bit of heat, adding about 3 to 4 milliseconds of overheads just to handling the software restoration costs. Because we have to cut off the processing early to keep the CPU in check. The culling efficiency is definitely lower than what the hardware can do. We are seeing about 2,000 colored versus over the 3,200 with hardware queries. Even though this is still a big step up from standard mobile-only solutions. That lower efficiency means our GPU cost actually goes up by about 1 millisecond. So, does this data mean that the hardware are just flat better than SDOC? Not necessarily. What we are seeing here is just the results of one specific strategy. To truly understand the potential of these different approaches in a massive open world, we didn't stop here. We kept digging in to see how we could push these boundaries further. To address the limitation we saw earlier, we initiated a series of optimizations specific tailored to NTE's architecture challenges. Our analysis shows that the original software culling failed because it wasn't designed for a world made of thousands of small meshes and instance static meshes rather than a few massive occluders. We started by overhauling how the engine finds occluders. Instead of traveling the entire scene every frame, which is a massive CPU killer, we maintained a dedicated occluder scene. By using a ECS style data structure, we kept memory access linear and avoid expensive virtual function calls, even significantly reducing the initial 1 millisecond traverse overhead. Next, we focused on the quality of occluders since NTE doesn't have many large single mesh walls. We implemented a system to merge fragment geometry, like modular buildings and rows, into large clusters. We also utilized the Omnio themed to its full potential by switching to code-based rendering, which perfectly fills the 128-bit registries and eliminates redundant edge calculations. Looking at the results on the right, these optimizations have led to marked improvement over our initial baseline. We've achieved a more balanced profile between CPU and GPU overhead, and the culling rate has increased significantly, reaching 3,100 primitives compared to the 3,900 from hardware queries. This brings the two methods much closer in performance. The software approach continues to offer the inherent benefits of zero latency results. Ultimately, if we move further to optimize the scene assets specifically around the characters of SDOC, there is even more room to push its efficiency and visual impact. After analyzing the data from NTE, we've achieved a critical conclusion. You can't simply label SDOC or hardware queries as better than the other. The choice is entirely a matter of which solution fits your project's specific architecture. It's virtual to decide on your culling strategy early in pre-production because it dictates how environmental art is built. For instance, if you are compared to GPU-driven pipeline, you actually want your assets broken down into smaller pieces to max the gradual efficiency of GPU instancing. However, if you opt to a software culling path like SDOC, your asset strategy must shift. You need high-quality occluders merging multiple smaller meshes into simplified clusters to ensure that a single software path can have a massive chunk of the world without choking the CPU. If your game bottleneck isn't on the CPU side, SOC is often the more robust choice. To summarize our experience, hardware queries are great for raw accurate, but the prone to latency and pipeline starters are mobile. SOC and especially optimized SDOC offers that much needed stability and zero latency performance, though it demands more discipline in how occluders are designed. In short, culling isn't just a technical toggle. It's an architecture commitment. By understanding the trade-offs in CPU overhead versus GPU latency, we can choose a tool that ensures Hexer remains both visual stunning and performant. Okay. To wrap up our optimization journey, let's look at a system-level tool, Snapdragon Adaptive Game Config, or SAGC. SAGC is the API for the Snapdragon Performant, broader Qualcomm adaptive performance engine. Based on telemetry, like CPU, GPU utilization, and thermal status, the game can intelligently downscale or upscale settings like resolution, FPS, or particle density. Additionally, SAGC can also be used to pass down case of overhead hence to SOC systems to adaptively adjust system results for optimal gaming execution. Implementing SGC involves integrating a specific work into the game's life cycle. It starts as app init and runs through the app close. The core magic happens during the game running physics. Every 1 to 2 seconds, the game performs a batch query for device stables. Once the game receives this data, the business logic decides the next move. To wrap up our discussion, we will dive into the final evaluation of these Qualcomm features alimentations, weighing the performance gains against the technical trade-offs and we encountered. The results across Snapdragon 8 Gen 2 to 8 Gen 5 speaks for themselves. We achieved a 38% power reduction with FME and a 12% bandwidth savings through SGS2 and tier memory keep. Where frame stability improved by 27%, we did observe a minor 12% increase in visual artifacts in complex scenes, though it remains with acceptable thresholds for over 19% of our test scenarios. Moving forward, our roadmap focused on deeper engine optimizations and expand devices support as new Snapdragon platform emerge. Ultimately, the strategy adoption of these technically precision NT and the technical forefront of mobile gaming, delivering a high-efficiency premium experience that differentiates us in a competitive market. Many thanks to our great colleagues. I want to thank the whole NTE team, thank Qualcomm, and thank the GDC committee. Thank you for your coming. We are thrilled to announce that the journey into the supernatural world of Hexer is just around the corner. A global launch on April 29th across all major platforms. We look forward to see you in game soon. Thank you. Lastly, on behalf of our partners of Qualcomm, I'd like to highlight their open source initiative and partner access programs. You can scan the QR code and leverage these resources to push the limits of your own game. Oh, okay, thank you.